Hello everyone, I am Dr. Brijesh Tripathi, working as Associate Professor at Pandit Dindayal Energy University, Gandhinagar. Today I am going to present applications of AI and ML, Artificial Intelligence and Machine Learning in optimizing industrial solar cell production. This presentation is based on the recent research work that has been done within my group. There are other members also, and in collaboration with Premier Energies Limited, Hyderabad. I have uh, tried to use artificial intelligence and machine learning techniques to transform solar cell manufacturing by connecting the data of wafer quality, thickness of anti-reflection coating, and surface textures with the output of the solar cell, that is its open circuit voltage, short circuit current, fill factor, and efficiency. The research papers related to this research work are also mentioned in this slide. There are many challenges in solar cell manufacturing. Some of them are listed here as light-induced degradation, that is due to wafer quality, then wafer thickness variability, reflection losses from the top textured surface, and process inconsistency. There may be some of the defects in the wafers which are ultimately affecting the performance output. Where we can apply artificial intelligence and machine learning, that is mentioned here. It actually AI and ML enables process optimization, defect detection, predictive analytics. We can predict some of the properties which are influencing the final results, and we can tune the parameters. Properties listed here are thickness of the wafer, resistivity, and carrier lifetime. Also, in another research work, we have used electrochemical impedance spectroscopy data, and that data is analyzed using some of the tools to find out the optimal thickness of the anti-reflection coating. From EIS, we can find out the electrical parameters of the solar cell that include series resistance. Then there are electrochemical parameters, we can say that, because there is junction capacitance in microfarad, and there is shunt resistance that is in kilo ohm. So these parameters are explored for solar cell by using electrochemical impedance spectroscopy, that is full form of EIS. Anti-reflection coating thickness data has been taken from the production line, and then the analysis is done. We can see here, without anti-reflection coating, the reflectance is very high, in the range of 8 to 10%. But with anti-reflection coating, the reflectance from the top surface of silicon solar cells is very low. Average value in a broad range of wavelength is around 1.3%. Machine learning can be used for incoming wafer quality calculations, or we can say incoming wafer quality optimization. In this case, we have started with data of wafer, which are raw wafers, their thickness data, their resistivity data, and their lifetime data. And that data has been correlated by using the models, machine learning models, with the output of those wafers when they have been processed to make solar cells. Open circuit voltage, short circuit current, fill factor, and efficiency. So the correlation has been studied, and the model first trained with some set of data and then tested for predicting the output for a given range of these input values, and then it was verified by using actual data of industry, and we could get quite good level of accuracy that I'll discuss here. So there have been 3 clusters, 1, 2 and 3, based on the classification that is discussed here. The wafers group, which were ranging in the with the peak value of around 153 or 54 micrometer, is cluster 3, and sharp value around 160 micrometer, cluster 1, and broad value with peak around 165 micrometer is cluster 2. Corresponding values of resistivity and lifetime are also for those same clusters. This figure is showing the variation of electrical parameter output of the solar cells, and here we have connected the electrical input parameters of wafer with output parameters of the solar cell. So we can see that resistivity for the clusters is increasing, and lifetime is having a peak value, and thickness is having peak value for cluster 2. Similarly, here in this figure we can see that open circuit voltage is going towards lower side, but there is not very big variation. It is around lowest value is 692.8 millivolt and maximum value is 694 millivolt. And efficiency and this efficiency and fill factor, they are maximum for cluster 2. So this result is showing that there is a particular thickness range with a particular peak value having a given value of resistivity and carrier lifetime, which is performing best in terms of efficiency and fill factor. This is another research work in which we have used surface texture data with respect to pyramid texture and their optimal values in terms of the height of the pyramid and the angle of the pyramid. We have correlated with the output parameter of the solar cell, that is the final efficiency, and includes open circuit voltage, short circuit current, fill factor and efficiency. We can see that there is a critical insight from this study that if the pyramids are steep, they will show minimum reflectance. But there is an optimal value that is in terms of whether we can manufacture easily in the production line a given pyramid or its steepness or its angle of steepness. So that is also important, that question whether it can be adopted in production line or not. So the models that we have used, random forest model and k-means clustering. Other models are also there which can be used for the prediction of cracks or detection of the cracks, classification of the defects, and power output can be predicted by some other models also. But in these research papers which we have referred, we have used k-means clustering and random forest model. So random forest model has provided 78% accuracy on the experimental data for texture optimization. This work was for the pyramid texture on the surface of the wafers, and k-means clustering was used for the correlation between incoming wafer parameters and the final performance of the solar cells, and in this case 99% accuracy was achieved. There are many benefits of machine learning integration with the production line equipments. It can improve the yield, it can assure of the quality of final production. Then data-driven manufacturing may be quite beneficial for achieving superior performance and yield of the overall line. production line. There is also process control can be identified in a better way if we are having the correlation information. One case study we have taken data of the wafers as thickness, resistivity and lifetime. 5,000 wafers data was input for our study. And then we have identified some of the features. Then we did model training, process optimization, and then real-time feedback. That means part of the data we have used for training and a part of data we have used for testing. The data that is collected for training was done by using these instruments: SemiLab, WMT1 for thickness and resistivity, micro photoconductive decay, that is for carrier lifetime, HAM IUCT 5000 for IV matrix, current voltage measurements, and AutoLab we are used for EIS, electrochemical impedance spectroscopy measurements. In case of pyramids, ML classification model categorized pyramid types and lowest reflectance achieved for type 5 geometry. For details of the types of pyramids, we need to refer the detailed research paper. We have also used PC1D simulation software to generate more data for validating the machine learning model that we have applied. There is in future we can say that if we are integrating AI pipelines in solar fabrication factories, we can reduce the cost per watt and increase the efficiency by real-time predictions of the parameters. The relevance for industry, we can say that models trained on 1 lakh wafer dataset will enable scalable smart manufacturing at reduced testing cost. So the preliminary study was done with a small dataset, but for smart manufacturing, we need a bigger dataset to train the model and predict some of the information which is crucial for manufacturing at reduced cost. Solar cell industry can be impacted by machine learning assisted design because we can expect by optimization the efficiency can be improved in the range of 0.5 to 1% if input material is optimized based on the predictions of machine learning. In global context, bifacial PERC solar cells with AI optimization may dominate greater than 30% of PV installations by 2030. This is an estimate. And we expect that at a field level, in the bigger power plants, mega or gigawatt scale power plants, almost 10 to 20% higher yield can be reported by adopting to machine learning based optimizations. Defect detection can be done by deep learning models, convolutional models, and electroluminescence images can be used to predict cracks, impurities, shading defects. No human interaction will be required if we are adopting to deep learning based systems for defect detection. Or it can be very minimal human interaction required at that stage. Then there are some other tools which we have not yet explored, but they are having high potential, like CNN, ANN, Deep Q Learning, PyGRU. So these also can be used in future studies. Based on our research work, I can recommend to apply real-time machine learning analytics in production line For greater insight about the dependence of output parameters on input parameters, dataset updates are required regularly, and also we can integrate the electrochemical impedance spectroscopy system with optical tools uh, for artificial intelligence based models. Final conclusion is artificial intelligence and machine learning are very important for next generation solar cell manufacturing. The team led by PDEU researchers showcased real industrial application in the recent research papers. In the first case, we have investigated the dependence of fill factor and efficiency on gallium doped silicon wafer characteristics using unsupervised learning. In the other paper, we have explored optimal pyramid textures using machine learning for high performance solar cell production. These are the related references in which these studies have been performed. We acknowledge the support received from Department of Physics, Pandit Dindayal Energy University, Gandhinagar, data provided by Premier Energies Limited, Hyderabad. For publications, we acknowledge the Springer and elsewhere journals. Also, we acknowledge the support in terms of funding that we have got from the university and from the government of Gujarat and government of India. Thank you for your attention.